We go to the surface charge. How can I analyze a surface charge? The same thing, I want to find the electric field at certain point, but here our source is not a line charge, but we have the surface charge. Okay, here the electric field intensity due to a surface charge can be defined as this expression. The only difference is we change this part because this is our Q or dq. In the integration form, you have here dq. So please remember, dq is depend on your charge system. If you have only point charge, so we can write as a q. If line charge, we have dq equal to rho L dl. Now we have surface charge, which is rho S ds. And another one, if you have volume charge, which is rho V dV. But for Coulomb's law, we only apply these three. Okay, this is very complicated. We are not applied for Coulomb. Alright, so we have a rho S ds. So the surface integration. So it should be more complicated compared to the line integrations. Let's see. Okay, almost the same thing. Okay, we have a circular shape, except we have a surface charge. Let's say this is a disc, a metal disc, contain of uniform charge density. Let's see the questions here. Find the electric field intensity along the z-axis on a disc with radius a located in the xy plane with uniform charge density rho s coulomb per meter squared. So everything is the same except our charge system is changed into surface charge. So let's say I want to find the E field here. What is the total E field at that point contributed by the surface charge? The surface charge contains a lot of charge. Right? That is the situation. So to solve this, okay, we have to write the general expression for electrical field intensity. Next, we have to take a sample charge. Okay? To solve this, we have to take a sample charge. Let's say I take this at this point, the blue color. And then the sample charge, we have to write down a vector from that sample charge to our point of interest. Okay, that is our vector R. Then we have to find out what is the vector R. Okay, this is using the concept of trigonometry. We have negative R in the direction of R and Z in the direction of Z. Okay, because it's going in, going up. Okay, that is the situations. And then write down all the related information, because we know here R equal to we can write as a Z minus RR. Okay, because this is negative, and the magnitude is actually square roots of Z square plus R square, and the unit vector, because you want to find what is the unit vector AR. AR is equal to vector R divided by its magnitude, so equal to Z cap Z minus R cap R divided by Z square plus R square. And similarly, we have to put everything inside our equations. Right. Let's say, okay, we have this sample of charge. Okay, this sample of charge, we have to understand how to determine the surface area of the disk, like we discussed in chapter 1. So the surface area is depend on the increment in r directions, because it depend on the radius. Okay, so we have dr, and then we have the curved part. Okay, the curved part is defined as rd phi. And then we can write the ds in this form, which is r dr d phi. Okay, so from here you see that the importance of understanding the suitable coordinate system and also the vector. So when you can come up with this correct coordinate system and vectors, now you can solve the problem. Write down everything like what we did for the line charge. So we have ds equal to r d phi dr or r dr d phi, which one is okay. And then we have the vector, the vector unit vector ar is equal to r vector r divided by r, and then here we have magnitude of r square. When you put everything inside this, okay, you put ar here and then the r here. This is a conclusion. You will obtain this form. So the integration of rho s r d phi dr divided by 4 pi epsilon naught r square plus z square, okay, the power of 3/2, and this is the vector r. Right. Similarly, we can separate, okay, the component into two parts, which is a component z and r. We have two components. So you can guess what happened next. Similarly, we have symmetrical behavior. Okay, since the charge is uniform and the shape is symmetry, so we have symmetrical charge. So let's say we take a sample here, and this sample contribute to the small E-field. Then we take another sample which is a opposite direction or 90 degrees difference, and this sample charge, okay, let's say this is a dqa and this is dqb, contribute to another small E-field which is deb. Okay, this is the situation. We can see that we have the r component of E opposing each other. So we can see that the r component will be cancelled out while the z component will be reinforced. Right. The same behavior. So what left is only z component. And now we have to solve these integrations. We have the integration of 0 to 2 pi d phi, because this is from 0 to 2 pi, and then our integration with r, we have r dr. From where? The r extends from 0 to a. And this form of integration is very difficult to be solved. So we have to use table. the table will be given. So this form, r divided by r square plus z square power of 3 over 2 dr is equal to this form. We have the rho sz divided by 4 pi epsilon naught. We have 2 pi, the integration of dphi, and then here you got this form, and the r is from 0 to a, so you have to fill in r equal to a and 0, and then this is what you will get. Z rho sz divided by 2 epsilon naught in brackets negative 1 over a square plus z square, the power of 1 over 2 minus 1 divided by z. So we can simplify this into this form. Okay, because we have z here, then we have z here. So we just rearrange into this form. Okay, this is the final expression for E. Next, similarly, what happens if our sheet become very large? Okay, is going to infinity. It's going to infinity. Very big. So what happened? Okay, this is a conclusion from our analysis. You have to change A to infinity. So the radius become very big. When the radius become very big, because the A is here, we have Z divided by something very big below. So what happened? So the divide here, Z divided by this form becomes 0. The divisions here becomes 0. So what left is Z rho s divided by 2 epsilon naught. Very simple. Volt per meter. In general, E is equal to N rho s divided by 2 epsilon naught. Because from here you can see that let's say we have the rho s on xy axis, so the vector is basically normal to the surface, is z. But actually it depends on the sign of our charge. It can be positive charge or negative charge. So we can write in general as a n, normal to the surface. The n can be going down. Okay. Electric field always normal to the surface charge. Okay, this is the behavior. Let's say we have the cylindrical shape, we have charge on the surface, so we can say that let's say at the top surface, so the E field going up, normal to the surface, and then we have the surface around the cylinder, so it's going normal to the surface, which is R directions. Okay, the direction R. And then here, find example, find the electric field intensity between the two parallel plate capacitor with infinite surface area. So this one you can do the derivation. because for the capacitor, normally we have the positive charge at one of the surface, and the opposite surface will be have the opposite charge. Okay, this is positive rho s, and then this is negative rho s. Okay, that's mean normally when you do the analysis, the conclusion is you will find that the E field will going down like this, normal to the surface. So you can see that the E field is from positive charge to the negative charge. And this is a definition of volume charge. Q is equal to rho v dv, and we can change the rho v dv here. As I mentioned earlier, volume charge system is very difficult to be solved using Coulomb's law due to its complexity. Therefore, we will not cover the volume charge for Coulomb's law. This part will be covered using Gauss law, which is using the much simpler approach to solve the problem related to the volume charge.